Hey, everyone. So my name is Hassan, as Andrea already mentioned. So today we're going to have some fun talking about how TCPX optimizes RDMA and GPU-Direct technologies. So just to kind of quick recap, refresher, RDMA is the direct memory access, which is the memory communication between one CPU host and the other CPU host without going through the operating system. And TCPX is a Google-developed and open-source software that essentially implements that technology. So my name is Hassan. I'm with Google. I'm a product manager there. And with me today is Hugo.
Nice to meet you all. I'm Hugo Huang. I'm the product in the Canonical side. So I think today we would like, it's very approaching the lunchtime. I know everybody is quite tired. So just to give you a very small task, can anyone figure out what's the problem with this picture? Hands up.
The handle.
Wow, great, great. Yeah, we'll deliver a chocolate for you afterwards. Okay, thank you. Yeah, this is the AI-generated picture, and at the typical unfortunate situation when you are, in the transfer of the airport, so everyone don't like the hops between flights. It's really, in the technical term, we call it the latency, right? It increases a lot of the latency, and maybe a couple of hours, maybe a few, maybe days. We don't know because it's latency. Yeah, that's the most saddest thing about when I come to The Hague. I transfer to Copenhagen. I stay there for more than 8 hours. So it's really, really bad experience. So anybody take the direct flight here?
Direct.
Oh, so fortunate. Yeah. OK. So we'll get into the RDMA. We'll tell you why it's so good to take less hops.
Yeah. All right. So, so this is a rough agenda of what we're going to be talking about today. But let's go into explaining why we need RDMA in the first place and what is happening when a host is talking to another host, specifically in terms of AIML workloads. So if you look at this kind of picture, there is a green line which is showing the intent of communication. So in a very basic term, when we are talking about the intent, we have a device memory, which could be any device. It could be a GPU device. It could be a camera. It could be any device you can think of. And what it's trying to do is it's trying to talk to another device in the destination host, because that's how the training is being conducted. That's the intent. Now, that's not exactly what happens in the real world without RDMA, of course. If we are using any AIML application, for example, running PyTorch or any kind of training, what is going to happen is that the device memory is going to talk to the operating system, kernel going to talk to the host memory. Host memory is then going to talk to your network card, transmit it, and the whole process is going to be reversed. So as Hugo was explaining, lots of extra hops involved in the communication between device memory to the other device memory without RDMA. Now, that's one of the problems. But if we look at some of the application use cases, so in some cases there's a file being transferred, let's say from a camera to on the other host side. It's just a file. It doesn't require CPU to be processing it, right? However, if we are using it without RDMA, that's exactly what's going to happen. CPU is going to find a memory block in host, go through, the host is going to assign the memory block, go to the network card, and so on. So that's really the problem that RDMA is trying to solve. It's trying to make sure that the actual communication is happening based on the intent. And here the intent is that we don't need any operating system processes or the host memory to process anything. So let's look into a little bit more detail. Hugo, do you want to?
Sure. This is a very basic logical graph about diagram about how the communication goes. First, you'll see on the left side it's the traditional network. Then your application initiated the conversation, and then your OS kernel will get involved to prepare data for transmission. And then you'll go through the session, go to the transport, go to the network. So all the 7 layers of the TCP protocol, you will go through everything. And then that's the first from the hosting machine, and then the receiver will need to get through the same process. It's a lot of hopes that you expect a lot of the delay and latency. But in the RDMA, in the right side, you can see that we just pass over the. Could you click again?
Yeah.
Okay. Yeah. We just pass over the 3 layers. We don't get involved in the presentation, session, transport. So the application initiated the conversation, and then the network driver, the NIC card, just start to communicate with other card. So we dump the data from the one host to another one. So this is quite the benefit we can get from the RDMA.
Great, thank you, Hugo. So the whole concept of RDMA here is to improve on 2 things. One is to provide the maximum throughput for the application communication, and second is to do it at the lowest possible latency. How does it do it? Essentially, the whole concept is to keep the data transfer at the lowest possible layer while keeping the control channels being at the application layer. So the reason we built TCPX is because it's a software implementation, and we're going to talk a little bit about later why it's super flexible, because it's not dependent on a certain type of hardware to be used. And how TCPX operates is shown here. Basically, we talked about the intent, that the intent is for the device memory from one host to talk to the device memory on the other host. And how can we reduce the number of hops here, which is also going to improve the throughput. So how it happens is that the applications on both sides are responsible for creating the control channel. And this control channel is essentially a wake-me-up control channel, which means it only gets activated when the application on host 1 is going to request it. It's not always open. So it's a very dynamically created channel, which essentially also makes the communication very efficient. So once the application on host 1 goes and creates this control channel, the data channel is built between the 2 NICs, and the NICs are directly then talking to the device memory. So in simple terms, we have bypassed the host memory from this operation completely. And as we were talking earlier, we had 4 hops from talking between these 2 device memory, and now we have basically 1 hop to talk between the 2 memories. So I think it's important to say that all of the data packet payloads are still TCP packets. So they still have the same payload, same headers and whatnot. But all of the packet transfer is happening at the data channel, not at the application or control channel. So let's get a little bit into details on, I know I said earlier that hey, TCPX is a software-based solution. There are other solutions in the industry that are built by many other different vendors. Some of them are software-based, some of them are hardware-based. One very famous one is InfiniBand, which is used for GPU-Direct. So here, Hugo is going to talk a little bit about TCPX versus InfiniBand.
Sure. This is a graph, very obvious that you have to connect all the network cards, each one. I think this is good because it's a fully mesh, and you can ask each of the card to talk with any of the other one, directly. This is very efficient, but also it's some difficult, problems we will have. That means you have to wire them by yourself or by some of colleagues. Imagine, Hassan, you're from Google, right? Suppose I want to rent like 100 GPU from you. Will you go to the data center wire for me?
Not really, no.
Oh, okay. Okay.
If you pay me, but anyway.
Okay, how much I need to pay? Yeah. Could you explain to the audience what is the DCN?
Yeah. DCN is basically a dynamic core network. And what it does is it's a mixture of the packet switch networks that we have in the modern networking and the circuit switch networks that we used to have with the telephones. So what essentially DCN does is if you have like a, let's say, basic fiber optic connection between two different cards, DCN is dynamically creating and destroying channels within that physical connection so that your applications and the hosts, they see a virtual channel as almost like a physical channel. But what DCN can do is, let's say you have a 200 gig physical fiber connection between two different devices. DCN can take that 200 gig bandwidth and it can slice and dice it however they want. So you can create a 50 gig one channel, 100 gig another channel, 50 gig third channel, or you can create 4 channels of 50 gig each. Why it's important is because when we are running it in a host, you will have many applications probably that are using that bandwidth, the same physical pipe, right? But what's important is that to avoid the noisy neighbor problem between the applications, which means that, hey, if I give the whole 200 gig to application A, and it starts using all of that, now my application B's throughput is going to suffer. So really, the whole concept of DCN is to manage the physical connection in a more circuit-switched, virtualized way.
So in other words, may I understand it's in any place of the world of your data center servers, I can make sure there is a direct connection between each other, about 200G at most.
Yes.
So it's like I can, logically hardwire any of the server from any of the data center of the Google that make it have the similar experience like hardwired.
Exactly, and not just Google, but also your on-prem other data centers, because DCN can be run on wide area network. It can be run on any logical network. It's a layer on top of an existing network.
Okay, that's good news. So
yeah. So you can make your on-prem network look like it's sitting right next to your Google network in the same data center, even though that's not the case, physically speaking.
Oh, great. So you don't need to wake up at 12 o'clock in the evening to hardwire any of those cards. That's great. Yeah. Speaking of the software, the advantage of software and advantage of the open source, we will see other problems of those hardwares because it's very high cost, right? There's only one vendor, so far as I know, only one vendor can provide those cards, and it's very expensive. Even I just searched this morning in the Google, I find that even those wires, you have to cost you more than $200 for each wire. Yeah. So it's very high cost, and also because you need to learn by yourself, or learn your employees have to learn these new technologies by themselves. You cannot actually leverage your existing knowledge and your existing networks. So that's a very expensive operation and management cost. And also, the worst thing about this kind of the only one vendor can can do that. You get a vendor lock-in. That's the essence of open source, right? We don't want to get vendor lock-in.
Exactly. So Hugo, what exactly is InfiniBand?
I don't know. I don't want to know that now.
All right. So I'll tell everybody what InfiniBand is. So InfiniBand, I keep calling it InfinityBand, but InfiniBand is essentially a wire between two GPU cards. It's an optical wire that is creating a connection between two GPUs. It's a somewhat newer technology, and it's trying to do the same exact thing that RDMA is trying to do, which is a direct communication between two devices, in this case, GPU. But as Hugo said, and as many of you would understand, that nobody wants to go to the data center, or even if it's not a data center, if it's your cloud deployment or whatever kind of server deployment in the basement, for example, nobody wants to go and start creating those wire connections between the two cards. So it's expensive and it's time consuming. So that's really what we are trying to solve here with this open source project, that you are able to leverage the same benefits without having to do the expensive efforts. All right, so let's talk a little bit. We have already talked about the advantages, but let's get a little bit more into the details of them. So why is TCPX better, right? Like we have talked about RDMA. There's many different vendors who are implementing RDMA, some of them through software, some of them through hardware solutions. The biggest benefit of TCPX is that we thought about it to be sort of an open implementation of this technology, meaning we don't want to lock anybody into any sort of vendor. So the first biggest advantage of TCPX is that it's more adaptable. It does not care about the hardware. You can use this to have direct memory connection between two regular memories or GPUs or any other device that is created in the future. This technology can be used to create a direct connection between those two. Some of the advancements, because it's based on TCP, and TCP also is obviously evolving with their own improvement in stacks, naturally TCPX becomes better and better over time because it's leveraging the TCP technology itself. We already talked about how it is less demanding on the hardware compared to the other RDMA technologies. This is one of the most fun point, the next one I'm about to make. This is a unique capability of TCPX, which is the receiver and sender sides are very independent. So if, for example, you have control of the sender and don't have control of the receiver, you can implement TCPX only on one side. So the optimization is on one side. Granted, you're not getting the full benefit of it, but you're still saving a lot of host memory on the sender side. Same applies for the receiver side, too. You can actually implement it on one of the two sides to get the benefit on the specific side. Because obviously it's using TCP, so the other side can still decode your packet. It's just going to have to go through the operating system layer and so on. And then finally, we talked about the hardware versatility. You can implement it on pretty much any device, whether they are NICs, whether they are GPUs or whatnot. So Hugo, do you want to tell us a little bit more about other benefits, real quick?
Well, I think the most important thing I consider is that you have the capability to scale it. So when you have you normally won't do like only 2 GPUs, right? In most of the case, you do like at least dozens of or hundreds of. And in the extreme cases, we found recently a use case that people would like wire like 4,000 GPU together.
Yeah.
And at the most, at Google, there's a lot of people are using TPUs because TPU is cheaper and sometimes more powerful. but some people also want to connect GPU and TPU together. So that means you have to have a protocol that works on both sides. So I think this is another benefit of TCPX because it works with both technology.
Yeah, that's great. So let's talk about all of the advantages in action. A very typical use case where you have multi-host distributed training running in Google's case with A3, which is a machine family that has A100 GPUs. Very similar discussion or design as we were seeing earlier, that you have Nickel, which is a GPU library, going through the user memory, kernel memory, and essentially what we are doing here is that the GPU memory is directly talking to the NIC rather than going back to the user memory and the kernel memory. So pretty much the left side of that red dotted line and the right side of that right dotted line, well, no, actually, just the left side of this red dotted line is not being used. GPU memory is directly talking to the NIC, and on the right side of the right dotted line is where it's being received. So a pretty simple use case. But the point that we're trying to make here is that if you take this use case, this is obviously talking about 2 hosts. Most of the machine learning and HPC workloads are going to be running on thousands of hosts, if not hundreds. Let's look at the bigger picture. That's when we can see the real benefit of it.
Yeah, true. At the bottom, you see that's the case we were just describing you about the 2 hosts. But actually, if you imagine a data center or multiple data centers, you will see so many GPUs, so many TPUs. The throughput is like a petabyte scale. So it's very, very difficult for. I can't imagine anybody have the technology, have the capability to hardwire so many GPUs together. I don't think even it's possible. It's not really scalable.
Yeah.
So, yeah, I think that's the best benefit of the TCPX. That's because it's avoided from vendor lock-in and avoid you getting so many daunting tasks about you get easy to get mistakes.
Great. So finally, let's talk about TCPX and open source. So we actually worked very closely, when we were designing this with a bunch of device vendors, at least in the beginning. But our vision was always to make it an open source project so that it can be utilized anywhere without getting vendor locked. So right now we work with Canonical to make it part of the Ubuntu kernel that runs on GCE. But TCPX is available in open source for both contribution and use. I think the biggest point that comes into picture here is that it's not dependent on a specific type of hardware or the specific company that makes that hardware. Similarly, in the essence of open source, we encourage the community to go and add to the upstream code. Essentially, a lot of it is to make it more device aware. So when we are talking about how to implement TCPX on your host, it's a package, it's a set of libraries, you implement it on a host-by-host basis, but it needs to be aware of what kind of hardware you're using it on. So that's the biggest piece that we want open source contributions on.
Yeah, sure. That's why we're together. So Google open sourced this project, and Canonical Ubuntu support all the latest hardware and software that enable this.
Awesome. And it's actually something that we have known that many enterprises and startups who are not on Google Cloud have actually been using TCPX to improve their communication, make it more efficient, both on-prem and on other clouds. So I think that's the biggest, I would call, win for us, that it's something that is being used outside of Google as well. So I think with that, thank you for listening to our short talk here. We really appreciate your time.
Thank you. I hope you're always get one hop flight to your destination.
Always one hop.
Hassan, Hugo, thank you very much. Now it's that time. We still have a couple of minutes for some questions. Let's see. We have the 2 mics. Is there any question in public? There is one coming in.
Yes, hello. I had one question about security. How do you, are there some other things you need to take care of for security, or is it taken care of by TCP as normal?
Good question. So because we are creating a data channel on a lower level, the security is still the job of the application. So if you are going to send encrypted packets, they are still going to remain encrypted packets that needs to be decoded on the other side by the receiving application or the device memory. So for TCPX, it doesn't matter that what kind of packet you're sending. It could be an encrypted packet, it could be a non-encrypted packet, but because it's doing the job at a lower level. Hugo, you want to add something to that? No?
No.
Okay.
Okay, thank you.
Yeah.
I think we are running out of time. Okay, that's the last question.
My question is related. Actually, you mentioned that DCM is.
Yeah, we can hear.
I think we can.
You mentioned DCN is working like a switch, and is it necessary to make any implementation? Is working like a layer 2 or let's say drivers? We can use it, or we need special software for that to make
DCN.
on-prem,
DCN, yeah.
especially for TCPX. It's related with that.
Yeah. So it's a separate set of libraries that enable that communication. So yeah, you're going to have to use it. But in a lot of modern host and operating system, it's available by default because DCN is still important even if you're not using TCPX. So it has many other applications as well. So yeah.
Thank you both for your talk, and if you have further questions, probably you can find them around the summit.
Thank you so much.
Thank you.
Thank you, everyone.